Let's get going. Good morning, good afternoon, good evening, everyone. It's a great pleasure to welcome today's speaker, Pavel Kroupa, who will talk on recent progress on dark matter, gravitation, and the cosmic microwave background. Pavel is a Czech-Australian astrophysicist and a professor at the University of Bonn and also at the Astronomical Institute of the Charles University of Prague. Pavel grew up in Czechoslovakia, Germany, South Africa. He obtained his doctorate from the University of Cambridge in 1992 with a dissertation on low-mass stars in the Milky Way. Pavel then worked at astronomical research groups in Heidelberg University, Max Planck Institute of Astronomy, and the University of Kiel before taking up his present position at the University of Bonn. There he leads the research group on stellar populations and stellar dynamics. Pavel has made very significant contributions to the study of distribution of stellar masses, dynamics of star clusters, dynamics of satellite galaxies, and evidence or lack thereof for dark matter in galactic and subgalactic systems. I greatly admire him personally for his courage in standing up to the dark matter paradigm in astrophysical systems whenever actual data supports his stance. Great to have you with us today, Pavel. Over to you.
Thank you so much. And so I want to give a broad sweep overview of the results on dark matter, gravitation, and CMB, which maybe are not so mainstream. This lecture is based on a talk I gave at UNAM in Mexico on the 1st of October. So it's very, very similar actually to that. I just wanted to acknowledge that situation. And now let's begin. So the standard model of cosmology is based on two fundamental assumptions, as everybody knows, and that is that Einstein-Newtonian formulation of gravitation is valid everywhere and all matter is created at the Big Bang. And so that model is confronted with observations, and the observations would be CMB and galaxy rotation curves, as well as, of course, other data. One finds that this model does not work. It's basically falsified, and to save it, one does have to include auxiliary assumptions. So inflation, one is to propose that there is inflation, that dark matter exists, and dark energy. And important here is to note that this dark matter component can be called warm or fuzzy or axion. It doesn't really matter because the adopted dark matter must account for galactic rotation curves and dwarf galaxies. This sets very stringent constraints on what these on the wavelengths essentially of these particles can be. So in particular, the dark matter density is there with fairly well constrained alone by rotation curves, for example. So you can't change this like dramatically to some completely exotic different types of form. They have to be basically dark matter particles. And so we want to test this model. That's the job of our scientists. Rather than just believing this construction is correct, we can test for it. And the core pillar of the model is, of course, this dark matter. And this dark matter has not been found in direct searches. Is there a way to test for it without actually finding evidence for the actual dark matter particle in a laboratory? So we know that dark matter must be particles in the standard model of cosmology that only intact gravitation. That's how this model is defined. Okay, that's where we have all the quantification of structure formation in terms of the dark matter being particles with these properties here. And so how can one test for this dark matter? And the test is actually very simple, and it is somewhat surprising actually that the community has not been doing this test. I like to refer to it as the Winnie the Pooh test. And so knowing the physical properties of the dark matter halos of the various galaxies from lambda-CDM theory as well as from observed rotation curves, we can apply this Winnie the Pooh test to test if dark matter particles exist. And the Winnie the Pooh test is just a cute name for the Chandrasekhar dynamical friction test, but it goes back to a story where there is a village which claims there's a huge pot of honey with invisible honey, so it's very special honey, and Winnie the Pooh loves honey, so he goes to this village, and one is not allowed to touch this honey, so he devises a test, and the test is just to throw a little stone into it when nobody's looking, and if it's empty, then it will fall down and do clonk. But if it's full of honey, which is not visible, then of course it will sink down slowly and one will not hear anything. And so that's the basics of the test. It's completely basically trivial. So a massive object moving through an invisible fluid. So in this case, the dark matter particle distribution will slow down and fall to the bottom. So he did the test, proclaimed there is no honey, it's a scam, and was expelled from the village because, of course, the villagers like the tourists to come and bring in money to see this amazing pot of honey. So that's the story. And so dynamical friction is something which every, I would really want to say kindergarten physicist should actually know about. It goes back to the seminal work by Chandrasekhar in 1943. In the context of a massive object moving through a distribution of background stars. So he did the calculation, published this paper. And the Standard Model of Cosmology with the dark matter halos around galaxies now actually predicts this new phenomenon. If dark matter exists, then Chandrasekhar dynamical friction on this dark matter halo must occur. Okay, this is inescapable. Okay, so we have this visualization. We have these are dark matter particles in the host dark matter halo, for example, the Milky Way. And this is a dwarf galaxy with its own dark matter halo, and it moves through this population of dark matter particles, and the dark matter particles are gravitationally diverted on hyperbolic orbits around this dark matter halo here, around this dwarf galaxy. Okay, so we then just have to integrate over all these encounters. So what happens is that when this galaxy interacts with this dark matter particle, the dark matter particle is in a hyperbolic orbit along this direction, and the galaxy now receives a nudge into this direction. And so its velocity vector moves up. It's still the same length because momentum is conserved, but you can see that this projection onto the original direction is now shorter. Okay. Then in the next instant, it has an interaction with the dark matter particle on this side. Again, the same thing happens. And this length is now the same as the previous length, which is now shorter than the original one. And again, it's shorter on this projection. And so the important point here is that these transverse nudges cancel out because there's dark matter everywhere around the galaxy. And so systematically, when we do this integration, systematically the motion vector of this galaxy gets reduced more and more until it is very slow. And so this can be calculated. This has been done in research papers, in books. So this development of the dynamical friction equation of motion is based on Binion-Tremaine's 1987 version. It's a very nice development, very simple, but very, very nice, and one can follow it. So I did a YouTube video on this because the dynamical friction is extremely important. So one can find this on YouTube if one wants to go through the details. I'm not going to go through the details here because it's, as I say, basically physics kindergarten knowledge. And so you can already see that this is the hyperbolic trajectory of the dark matter particle around the galaxy here. And this original velocity vector now gets a component into this vertical direction. And so the original velocity vector gets reduced. And so one just has to then calculate the integration. The vertical components cancel out. The parallel ones add up in a negative way. And so one ends up with a dynamical friction formulation here, and I'm just skipping through these details, but one gets this equation. So this is the deceleration, the rate of change of the velocity of this galaxy. This is a negative sign, as a consequence of the velocity of the galaxy in the dark matter halo and the dark matter mass density over here, and that's the mass of the dwarf galaxy or the other galaxy. And we can now calculate with this deceleration how a orbit decays. So this is just a talk on such a orbit of a dwarf galaxy, and we can calculate how quickly the angular momentum of this orbit disappears. That's done over here, and we get the merging time or the mass segregation time scale. So the massive object sinks to the center. It's basically the mass segregation process versus the low mass dark matter halo particles. And so we have this time scale, and we have an equation of the deceleration, which we can put into our equations of motion. So we can now look at this equation. So that's the setup. We have the host dark matter halo. That's our dwarf galaxy coming in with a velocity, which typically, this is just empirically, the velocities are typically always comparable to the velocity dispersion of the dark matter particles in the dark matter halo here. So, which is about the circular velocity, more or less. And this is the initial radius, which enters there. That's the velocity dispersion, and so we can calculate how quickly this takes. So if this is the ratio of the dark matter halo mass divided by the mass here, so this mass here is that quantity, this mass is that quantity, then we can see that if eta, so if Fm is 1, so the two are equal mass, which is basically pushing this approximation to its limits. Remarkably, it works surprisingly well compared to numerical simulation. So when the two masses are equal, the merging time, so the time it takes to arrive at the center, is about half the crossing time, which is just the free fall time basically through the system. And when it's a factor of 10, so when this is 10 times more massive than the incoming galaxy, it takes about one crossing time, so going once through. That's about the time scale for them, for the merging here. And so if there is dark matter, then there must be Chandrasekhar dynamical friction on the dark matter halo. Okay, so we have this visualization, as I said before, there's a galaxy and it has this dark matter halo, and the other galaxy comes in with its dark matter halo. And so this is what I just mentioned. We have this equation of, so the other way of how to interpret this or visualize this is that as this galaxy moves through, it produces this dark matter wake, an over density of dark matter behind it, just because of these deflections. And colloquially speaking, one can say that this over density pulls back at this galaxy, and so it gets slower. So that's another version. This dynamical friction force, acceleration, is this equation which we've had just now. And the important thing here is that it depends on the dark matter mass density. So while these particles have mass m, the density, the mass density, is given by the theory, the lambda CDM theory. So this is not a quantity we can choose arbitrarily. It is essentially given by the rotation curve of the galaxy. Okay, so that is a fixed quantity which we actually get from observations through the rotation curve of a galaxy or from the theory. And this test is insensitive to the mass m of the dark matter particle, which is why it is so very robust and powerful. This can be WIMPs, it can be dark matter, it can be black holes, or it can be axions, or even fuzzy dark matter, as long as this dark matter model, which one is entertaining, explains even the dark matter in the ultra faint dwarf galaxies, which are very small. Okay, so that also has to be always understood in this framework. Okay, so here's a visualization again from Beginning to Remain, the second edition now, where we can see that if the velocity of the incoming galaxy is 3 times bigger than the velocity dispersion of the dark matter halo, we have this wake of dark matter over density behind the galaxy, which is moving into that direction. If it's slower, if they are comparable, then this wake is much bigger. Okay, and so we have a much bigger effect with velocity. So this deceleration gets smaller the faster the velocity is of this incoming galaxy, and this is nicely depicted by this graph here. So that's our picture here, and therefore the velocity vector gets slower, and we have this dark matter halo wake behind. And ultimately the galaxies merge. So this is why galaxies merge, but only in the dark matter theory, because if the dark matter halo is not there, then the galaxy would just pass through and go out again on a hyperbolic orbit. Okay, so the merging is an essential aspect of this dark matter based model. And so we have three ways of doing estimates. We can use this analytical estimate. So we observe a system on the sky. We have an estimate of the separation of the galaxies. We have a mass estimate from the mass luminosity of the one galaxy, and we have an estimate from the theory and the rotation curve of the velocity dispersion in the other galaxy. And so we can quite nicely estimate how long it would take for the system to merge. We have the semi-analytical way to do it, where we can actually integrate the equation of motion through a dark matter halo using this Chandrasekhar dynamical friction formula. And we can do the full simulation where we integrate the galaxies with their full life dark matter halos, like in the Illustris or Eagle cosmological structure formation simulations, where they then interact fully lively. And so we have these three different ways of estimating the effect of dynamical friction. And here's an application. This is from Van den Bosch at Yale University, where we have the dark matter halo in red with the dark matter particles, and a galaxy A enters, and then it spirals in and reduces its distance to the center over time. Now, this is the reason why we have the merger tree, right? So the galaxies merge because of exactly this effect. Otherwise, they would merge. Otherwise, this dark matter halo would not merge with this one. Most likely, it would just fly through and orbit around it, or even be on a hyperbolic orbit. And this dark matter halo, which is quite far away from the from this one, would just go through and out again. Okay, and the reason why we have this merging is exactly because of this dynamical friction. So why do they merge? Precisely because of Chandrasekhar dynamical friction. That's the essence of the dark matter-based cosmological models. And then this opens up immediately the question, why, if there's all this incredible amount of merging, why are real galaxies mostly disk galaxies? The answer to that is they can't be, because these mergers destroy disks. This has been published. And the reason that there are real disk galaxies out there is because there is no dark matter, because all this merging is not actually happening. Okay, but let's get to that conclusion within this talk. So here we have a simulation by Ogier and Burkhardt. What we are showing here is a projection of a dark matter halo where the density is divided by the density at that point. So by the original density at that point. So this is basically an NFW halo, and at each point it's normalized by the density at that point. So initially t equal to 0 is just green because the density contrast is 0. So it's the original density. Now a dwarf galaxy comes in, and you can see how it merges. So that's a galaxy, and it produces, it changes the distribution of the dark matter and merges within 2 to 3 orbits. Depends on the mass ratio, which is actually not quantified here, but doesn't really matter. The point is that you can see very nicely in this simulation the dark matter halo wake. So you can see this galaxy is now producing this overdensity, that's the dark matter halo wake, which reduces the velocity. Then, then as it orbits, as it continues to orbit, you can see that it produces an overdensity in the original dark matter halo, which also pulls back at it, right? So at this point here, this overdensity is pulling back and so on. And so you can see very nicely this effect in this simulation. And then we have here another simulation by Naab and Burkhardt of 2 disk galaxies, and you can see how quickly they merge within, actually in this case, 1 single orbital time, and they are merged already. And so we apply the Vinje-de-Poot test for dark matter on the small Magellanic cloud, large Magellanic cloud, Milky Way triple system. So before I continue with that, I do want to say and re-emphasize that this dark matter, this dynamical friction, is extremely well understood. It's in every serious textbook on cosmology. You will find a discussion of the dynamical friction test, because it's the core of the whole model. Without dynamical friction on the dark matter halos, you wouldn't get structure formation. As simple as that. Yeah. You wouldn't get galaxies actually forming and growing up, because they form and grow up through the mergers largely. And so here's now a test. Do we actually see this in the real sky? So here's the Milky Way disk. That's the large Magellanic Cloud, small Magellanic Cloud. This is the gas stream, which is called the Magellanic Stream behind it. And the leading arm is already also identified. And so we know from Gaia measurements that the motion is moving, both of them are moving in that direction, and the SMC is orbiting the LMC. So we have such data that we have, for example, the mass of the Milky Way, the stellar mass, the dark matter halo mass from theory or from the rotation curves of the Milky Way. We have the baryonic mass of the LMC with fairly large margins, which we take in this calculation, and the dark matter halo mass of the LMC, again based on the lambda CDM theory in this case, and also observations of the rotation curve of LMC and the small Magellanic Cloud likewise. So we have a broad range of the masses centered on the best value we have, which are these here. And then we have the position vector and the velocity vectors from proper motion measurements of the galaxies. I mean, these are now today so precise that with Gaia, the astronomers have detected how the LMC is actually rotating within it. Okay, so these numbers are pretty well known. And for example, the distance of LMC Milky Way is about 49 kiloparsec, and that's the velocity of LMC to Milky Way, which is pretty fast, actually. And then the distance of SMC to LMC is 22 kiloparsecs, and the velocity SMC LMC is 90 kilometers per second, which is about the orbital velocity around the LMC, remarkably, for its dark matter halo. And so we have these equations here, which I showed before. We know the Milky Way dark matter halo, this dispersion of about 220 kilometers per second. The dark matter halo of the LMC has a velocity dispersion of about 100 kilometers per second, and which is about also that rotation velocity of the SMC around the LMC, remarkably. And the analytical estimates tell us that the LMC will be merging with the Milky Way halo in about 370 million years at its present distance, if it were on a circular orbit. But since it's coming in and going through, and if it were at 110 kiloparsec, it would take about 1.5 billion years, which is about consistent with the first infall, as is often said. Now that's not so much the problem. The LMC in the Milky Way halo, in a first infall, it is understandable, but the SMC in the LMC halo, so the LMC has the companion, the SMC orbiting with it, and that merging time is only 250 million years if it's at the present distance, and if it were at 100 kiloparsec from the LMC, the merging time would be 1.2 billion years. Okay, and that is an issue. So the LMC and SMC binary should merge within 0.3 to 1.2 billion years. Now, this graph just demonstrates the dynamical friction, how important dynamical friction is. So this is the force. This is the gravitational force between the two galaxies, which is not dependent on the velocity between the two. This is if they are at a distance of 10 kiloparsecs. And the dynamical friction of the two, the SMC in the LMC dark matter halo is this red curve, which depends on velocity. And of the LMC in the SMC halo is this curve, which also depends on velocity. So at high velocities, it's negligible. At the velocities we observe them at its maximum, and you can see that it's very comparable to the actual gravitational force. So the dynamical friction effect is very significant for the orbital motion of the SMC around the LMC. So they are comparable, and that's why the dynamical deceleration is very significant in the orbit of the SMC around the LMC. And so this makes the development of the Magellanic Stream nearly impossible, because we need, in order to make the Magellanic Stream, the SMC and LMC must have had a close encounter about 1 to 4 billion years ago. That's a very, very liberal time frame we are giving this. And with this merging time of the two, it's basically impossible, because if they had an encounter 1.51 billion years ago, then today they should basically be already emerging, like pushing this to the near limit. And we therefore, with a program which Wolfgang Oehm developed, we do a parameter search using the Markov chain Monte Carlo method and independently genetic algorithm. Given the current constellation, we go backwards in time to see if we can fulfill these two galaxies to have had an encounter 1 to 4 billion years ago. So we go backwards in time, and dynamical friction then becomes an acceleration. And is it possible, given the current constraints on the distances and velocity vectors, for them to have had an encounter 1 to 4 billion years ago, so that the Magellanic stream could have been produced? And we know this is necessary from independent simulations of a number of other researchers. And we search these two most quantities, the velocity in right ascension, velocity in declination for LMC and SMC. So these are the quantities, and these are the search parameters which we allow to vary, and then we see which solutions are possible within the Gaia constraints, basically. And these are now the best solutions for the Markov chain Monte Carlo method, and this is the best solution for the genetic algorithm. They are basically identical. So this is a consistency check using two different search engines. We get basically the same solution. That's the best one can do. And so we can see that this distance LMC SMC, it's this faint curve, this one here. We have an encounter just outside of the 4 billion year window. And this best solution is therefore not formally a solution here. Furthermore, it is at more than 5 sigma outside of the observational uncertainties for these quantities here. And that's the case here too. So it's basically not possible to find a solution. I skipped over this too quickly. So there are no solutions within 5 sigma given this one constraint. Okay, and we do not find a solution. So that already excludes the possibility for the Magellanic stream to have been produced by an encounter and to keep the system bound. But the situation is much, much worse because of this research paper by the Canary group, the synchronized dance of the Magellanic cloud star formation history. So today we know from these people that the LMC and SMC have a synchronized star formation history. So what they did is they looked at millions of stars and constrained the ages of the stars. So this is the look back time, and they were able to reconstruct the star formation history going back in time. And so this is the SMC. You can see that the SMC has a star formation history which is basically completely flat over the age of the universe, the LMC2, but it has these wiggles. And remarkably, these wiggles are synchronized with the wiggles of the star formation history in the LMC. These are different fields they looked at. And these are the uncertainties. So the further back we go in time, the less precise it gets, because the stellar models become less reliable, because we're looking at low-mass stars which are evolving over longer time. But here, where the error uncertainties on the age estimates are reasonable to identify these type of wiggles, we can see a synchronization of these, which means the only way to explain this is that the LMC and SMC have been orbiting about each other for at least 3 billion years. Okay, so we can see that there were 1, 2, 3, 4 close encounters in the last 3 billion years, which means these two galaxies have an orbital period of about 0.75 billion years, with the period barely decreasing. And this is in contradiction to the merging time of this amount. Okay, so it's impossible to sustain such an orbit if there is the dynamical friction on the dark matter halos. And so here is the best one can do from the work with Wolfgang Oehm. So we have here the distance of the galaxies versus look-back time. This is the LMC SMC separation in the best solution one can possibly find given the dark matter halo properties of these galaxies. And this best solution, which is given by this red curve, is still excluded at more than 5 sigma confidence, given the observational data. Nevertheless, it is the best one can do, and you can see that it is completely impossible to squash 4 orbits into the time between 3 billion years and present day. If you'd like to squash this, so you'd like to increase the orbital period of the two, they immediately merge away because of the very strong dynamical friction. It's completely impossible to get an orbit which has a perigalacticon here, epigalacticon, perigalacticon, apogalacticon, perigalacticon, if there is this dark matter. And so there is absolutely no solution for the SMC LMC orbit that explains the synchronized star formation history. So a solution of this triple system is not possible in the Standard Model of cosmology. Therefore, since we see these data, there can be no dark matter. Now, we can look at the situation without dark matter. So this is the previous orbit I've shown, where the two, so that's the distance versus time, and the 3 galaxies, so the Milky Way is down here. It also reacts to the orbit. You can see that through dynamical friction, the LMC and SMC decay to present time. So that's the best fit solution, and this is now just turning off the dynamical friction. The calculations by Wolfgang Oehm, where the dynamical friction term is switched off, but we keep the dark matter halo. So this is a very primitive version of doing modified gravity. And then you can see that they happily orbit about each other and there's no decay. Okay, so they just orbit about each other, and the pair orbits the Milky Way, and there is very little decay because there's basically there's no dynamical friction because there's no dark matter halo, although the potential is there. And so without particle dark matter, 4 pericentric encounters SMC LMC are actually natural. Yeah. Okay, so this is one test, and it falsifies dark matter really very conclusively. Now, there have been other tests, so on galactic bars and the past orbit infrared solutions to the Milky Way satellite galaxies have been looked at. I'm not covering this. And there are perturbations of dwarf galaxies in the Fornax galaxy cluster, which was the previous talk by Indranil Banik. And so let's first now look at the galactic bars. So the Winnie-Pooh test for dark matter on galactic bars. Now, galactic bars are remarkable, very beautiful structures. You can see here a beautiful galaxy with a very major bar, which is very long, you can see. You can see this beautiful star formation, which is nearly semi-regularly spaced in the spiral arms, which is a very common feature. You can see these regular spacings. But this bar is orbiting with the galaxy. It's a rigid rotator. So this edge point, just go back, this edge point here is at the circular velocity of the galaxy. It's rotating with the circular velocity of the galaxy, and within that it's a rigid rotator. And so that rigid rotator constitutes a large amount of mass, and that induces again a wake in the dark matter halo. It's like a spoon stirring up, so we have this dark matter overdensity behind the bar in this rotation, and that dark matter overdensity pulls back at the bar. And so this overdensity now makes the bar rotate slower. And so a bar is like a spoon in a morning thick, dense, black, perfect coffee. Okay, the spoon, you put it in and it stops rotating because the coffee is non-rotational, largely. So the bar rotates like a rigid body. We have here now the velocity versus distance from the galactic center of a galactic disk, which is a flat rotation curve. We would expect Keplerian prediction, the decline. That's why we have to put dark matter in. The dark matter tells us the density of dark matter particles, which tell us how strong the dynamical friction is. And the bar can only exist in this part as a rigid rotator. And because of the dynamical friction, the bars slow down. The bar length then must shrink, because if it slows down, it can only be shorter to still be a rigid rotator. And so we can now test for the length of the bar compared to the co-rotation radius, which is this distance where the rotation curve becomes flat, in the theory with dark matter versus the real galaxies. And this parameter, if this is, so that's the ratio between the co-rotation distance from the center and the bar length. If it's larger than 1.4, we have a slow bar, i.e. the bar is short. If it's shorter, if it's smaller than this, we have a fast bar and the bar is very long. And this is here from the publication by Roshan and Gaforian et al., where we have here the Eagle simulation, so this galaxies in the Eagle simulation, and here the actually observed galaxies with the uncertainty contours. And you can see that they are completely discrepant. In fact, we see that the real galaxies here are fast bars because this quantity is around 1.4 is slightly shorter, smaller. So there are long bars in the observed galaxies, while the theoretical galaxies have slow bars because this quantity is large, and so we have slow bars. And this difference here is 8 sigma difference. So basically we have a falsification of the dark matter models at 8 sigma tension based on this test. And so the tests for particle dark matter halos are this small Magellanic cloud, large Magellanic cloud Milky Way triple system. Then we have the M81, M82, NGC 3077 triple system, which is the nearest galaxy group, which we've looked at. Then we have galactic bars. We have the past orbits in full solutions of the Milky Way satellite galaxies, which actually there are no solutions because the observed satellites would require dark matter halos, which are far more massive than the theory allows for them to get stuck in the dark matter of the Milky Way. And there's the tidal deformation of too many dwarf galaxies in the Fornax galaxy cluster based on the work by Elena Asensio et al. And as presented by Indranil Barnik in the last talk. And so we can see that always consistently and robustly, there is no dark matter. That's the conclusion. Individually by each of these tests and together, of course, is completely now convincing. So there are 5 independent tests. They agree the cosmologically relevant dark matter particles, cold or warm, are not present, which is also why they have not been found, and they will never be found. So it's a waste of money to keep looking for the dark matter. So now remember, the merger tree is an essential mechanism in the standard model of cosmology. The dark matter halos merge to form more massive ones because of Chandrasekhar dynamical friction, which is the topic of this lecture. So without this process, we would have in this model today no galaxies. But so the same process, however, makes observed galaxy systems impossible to exist. So we have a significant logical contradiction here. And without dynamical friction, galaxies cannot grow. So either we have galaxies and dynamical friction, or we have no dynamical friction and no galaxies in this approach, with this theoretical approach. Here's an overview of the standard model of cosmology. I mean, this already indicates that there's a really serious issue with this entire construction. And in this publication, we put together a estimate of the current likelihood of this standard model of cosmology to be still a valid description of reality. So this is the time where various publications have occurred, and that's the confidence. And what we say is we start with the confidence we believe in the model. So the confidence is high, that's our hypothesis. So Einstein is correct, Big Bang is correct, and then there's a failure, but we refer to that as the detection of dark matter. So we add dark matter, that's why this is black. Then there are failures, which are based on Kokas problem, angular momentum problem, and then dark energy. So the universe should be slowing down. It's observed to be expanding faster than it should, slowing down because of self-gravity. It's observed to be faster expanding. So one invents dark energy, which is allowed theoretically. So that's the discovery of dark energy. So that's not a loss of confidence. So these are not loss of confidence, a discovery of new physics. But then within these frameworks, with that theory, there's always loss of confidence because some key aspect of an observed system is not is falsified or intentional with the real observations. And each of these, there's a number, so you can look up in the catalog here to see which particular test it is, which particular publication is implied, and you can see that in some of the cases the drop is catastrophic. It's more than a 5 sigma falsification of the theory. This inset is just the inner part here up until 2010, so until this time, so it's just this part. But today we are even beyond this, so this is going up to 2023. And basically at that time, 2023, the LCDM model remains valid with a probability of 10 to the minus 130. Okay, so the standard model of cosmology is the most falsified but believed to be true model ever in the history of woman, man, them, kind. And this is the crisis. The crisis is not the fact that the model doesn't work. That's just scientific understanding, because it would lead us to develop new models. The actual crisis is the statement here. That's the crisis. Scientists continue to search for something which just doesn't exist, and they are spending a hell of a lot of taxpayers' money doing that. And that's the scandal, or also crisis in physics. So implications are, at this point, any serious dark matter physicist will drop their pen, turn by 90 degrees, and start thinking about non-dark matter models. Other implications are, the question which I like to ask students, are these merging galaxies? Yes, of course they are. Of course they are not, because if dark matter doesn't exist, then they are interacting galaxies which pass through each other. They perturb each other because they are quite fluffy. They lose some kinetic energy. They go apart. They might come back, or they go out on a hyperbolic orbit. We don't know. We are just catching these systems in a particularly strong encounter. They will not merge. This is not a proof of merge at all. It's just simply a capturing particular systems which are currently interacting with each other. That's all. So because there's no dark matter, gravitation obviously cannot be Newtonian in the non-relativistic limit. And so is there unequivocal evidence for this? I mean, this is the logical implication. If I'm saying there is no dark matter, then obviously dynamical systems must tell us, yes, indeed, we are seeing deviations from a Newtonian gravitation in those cases where we know that dark matter cannot play a role even if it were to exist. And so we are now addressing this question. Just now we deleted that from the equation. Now we are looking at this fundamental axiom. Is this valid? The core hypothesis of the model. Okay, and so is gravitation Newtonian? And we know from the work of Xavier Hernandez and Kyu-Hyun He on the work on very wide binaries that this already is very much in doubt. And now let's look at open star clusters. They lose mass. A star cluster, when once it's born, it loses its stars over time, so the rate of mass loss is negative. And how does that work? So in a star cluster, the stars have a velocity distribution, which can be modeled as a Maxwell-Boltzmann distribution to a very good approximation. So we have this distribution, that's these are the velocities of the stars in the cluster, that's the number of stars. And there's a tail of high velocity stars at any instant. Now, this tail is beyond the escape velocity from the star cluster, so the stars in this tail, they will escape from the cluster. And that leads to a decrease in the mass of the cluster. This tail, once these stars are gone, this tail is repopulated, and it's repopulated because the stars in the cluster move around in the cluster, and they exchange gravitational energy between each. Very, very tiny tugs of gravitation, but there are many stars, lead to some stars getting more bound to the cluster and the other stars absorbing the energy and being elevated in their energy until they become unbound. So they have a kinetic energy which makes them formally unbound from the cluster, and they then linger around the cluster, move around with the cluster, but this halo of formally unbound stars can't just exit. It needs to find an exit in the Lagrange point. So first of all, the mass loss, so the evolution of star clusters is very well understood. This is the seminal work by Holger Baumgart and Jun Makino, where we show here the mass in a star cluster going from 8,000 to 128,000 stars for different models for a King model and a distance of this solar radius from the galactic center as a function of time. So putting these clusters into the galaxy, but thinking now, just ignoring the stellar dynamical evolution, only looking at the mass loss from evolving stars, these curves for standard stellar IMF. So any stellar population with a standard stellar IMF loses about 70% of its mass simply through stellar evolution. And that's just basically given by the evolution of stars. If we now put these into star clusters, we get these curves. So first the star clusters loses mass from the stellar evolution, so it puffs up. Once it's done that, it goes on to the stellar dynamical evolution track, which is slower. So this slope, the rate of mass loss through stellar dynamical evolution, so through the energy equipartition process within the cluster, is slower the more massive stars there are, the more stars there are, and goes much faster if there are fewer stars. And this is extremely well understood just from the two-body relaxation process in the star clusters. So this evaporation from the star clusters is very well understood. And interesting here in this context is that the star clusters die by leaving highly hierarchical multiple stellar systems in the galactic field. So 3, 4, 5, 6, 8 stars orbiting about each other with similar masses in highly hierarchically systems. So the evaporated stars leave their open clusters through tidal tails. So we look at a galaxy from down upon a galaxy from the north. We look at this little box. The galaxy is rotating to that direction, which we deduce from these dark clouds here and the young stars on that side. So the galaxy is rotating like this. So we now look at this box, and there's a star cluster in this box. So that's the box, and that's our star cluster. The galactic center here is in this direction, rotation that direction. This star cluster has an inner and an outer Lagrange point, and the stars are moving around in there, and through the energy equipartition process, some stars gain energy over time and end up moving around here like zombies trying to find some exit, and they can't find an exit until by chance they get either through that point, which is the lowest point in the potential, or that point. Now, in Newtonian gravitation, these two are symmetric around the cluster at the distance of the Sun from the galactic center. So this is very well understood now. We have exactly the same picture. The star cluster is here, and now a star, call it a zombie star, finds this exit with a very small velocity. It's moving with the cluster, but now finds itself just over there. And because it's further away from the galactic center is in this direction, it's on a slightly elevated orbit, and therefore, since it's moving basically with the same velocity, it starts to drift behind the cluster. Because the circumference here is bigger than here, because it's at a slightly higher orbit away from the galactic center. So it can only drift backwards. There's no other way. Every star leaving here will go slightly backwards, drift slowly backwards, and because it's a slightly, if this is on a circular orbit, then this star is not on a circular orbit. It's on a slightly eccentric orbit, and that's why it does this epicyclic motion relative to the cluster. So it drifts behind. Because it's on eccentric orbit, it goes to epigalacticon, perigalacticon, slows down, goes with the cluster again, and then goes further away again on the next loop. A star which by chance happens to leak out at this inner Lagrange point is now leaking out of the cluster towards the galaxy, so it's basically falling towards the galaxy, and the only orbit it can have is one which takes it ahead of the cluster. because it's on an orbit which has a smaller circumference. So it slowly leaks ahead of the cluster, makes a and again, exactly the same process. This is on a slightly eccentric orbit, so it does this epicyclic motion and goes out and moves ahead. So since the stars can only leave there or there, we have a leading arm and a trailing arm. And that's extremely nicely seen in simulations. Andreas Kroupa, who did a PhD with me some years ago, discovered these overdensities. So this is a cluster looking from the top, and we see these overdensities, which are these epicyclic overdensities. They come at fairly regular distances. This is the same cluster seen edge on. We are now looking in the disk of the galaxy at the same cluster, and we can see these overdensities. So this is the Kuiper overdensities or epicyclic overdensities. We know very nicely, this is what I've just shown, how they work. They are, of course, not pinpoints, but they are spread out because the stars leave with slightly different velocities. And how do these work? Well, there's Jan van Altenburg has been looking at this in great detail. So we have here the cluster again, and a star which leaks out with a very small velocity relative to the cluster. That would have this type of orbit and have this epicyclic, tiny little epicyclic loop here and go off. A star which leaves with an even smaller velocity, in this case ahead of the cluster and back of the cluster, will go into these type of orbits. And a star with a much larger velocity difference will go into these orbits here. And so now, since we see these overdensities, this constrains very nicely the type of velocities with which stars are typically leaking out of the clusters. And this is a much higher velocity. Actually, it turns out that a star which is formally unbound can end up on an orbit around the cluster, not actually even finding a Lagrange point of exit because it's simply too fast. And so this is all very well understood. We do expect these overdensities for a particular velocity range of escape. This is now a calculation by Just et al. We see the cluster from the top again. It's orbiting to the left here now, and the galactic center is to the bottom. And you can see that the leading arm has these beautiful overdensities, the trailing arm too. And this is at a time of 1.4 billion years and 6 billion years, 5 billion years later, the same cluster has now lost a large fraction of its stars, so it's much smaller. And these overdensities have now shifted towards the cluster. You can see that the distance from here to there is much bigger than from here to there. And the same here to there, and from here to there. So the position of these overdensities relative to the cluster is a very, very important device to measure the actual mass of the cluster, but also, which we know from observation, because we know the stars in the cluster, and therefore this distance also depends on the galactic potential, as shown by Andreas Kroupa, and so we can extract the potential information of the information about the gravitational potential of the Milky Way. So the Kuiper overdensities are symmetrically spaced and the distances are smaller with smaller cluster mass. And in this paper, globular cluster streams as galactic high precision scales, Andreas Kroupa has quantified how if we have multiple globular clusters which are orbiting chaotically around the Milky Way, and if we can measure these overdensities, we can construct a three-dimensional image of the galactic potential, not of the dark matter distribution, because dark matter doesn't exist, but of the dark matter, but of the galactic potential. I think this is a really important publication which needs follow-up, and so we can use this to accurately map out in 3 dimensions the galactic potential. And this has been discovered. So this is the PAL 5 globular cluster. It's moving in that direction. The leading tail has these overdensities and the back tail as well. So that's actually very nicely confirmed by observation. But globular clusters are complicated because they are on chaotic orbits, on eccentric orbits, and so the tidal tails are, when the cluster is orbiting the front tidal tail gets squashed up at apogalacticon, and at perigalacticon they get drawn out, and so making measurements of the gravitation of the theory of gravity, concerning the theory of gravitation using tidal tails of globular clusters is not easy, and it's actually rather difficult and nearly impossible. So open star clusters, however, are on nearly circular orbits. And this simplifies the interpretation of their tidal tails. Photometric and astrometric data allow tidal tails to be mapped out using the convergent point method in open clusters. The recent advance in technology has been immense, especially with the Gaia emission. That has been a real game changer in this. Now, the previous student of mine, Teresa Hrabkova, has developed a new method to actually map out these tidal tails to their tips. It's the Hrabkova compact convergent point method, published in this paper here. And with that, Hrabkova et al. Published the tidal tails of the Hyades star cluster. The Hyades star cluster are 45 parsecs away from us. They are on a fairly circular orbit around the galaxy. That's the motion vector, so that's the image on the sky we have. Each is a real star here, which is a highly likely member of the Hyades, and notice this awful overdensity here. The asymmetry, which we detect now, is 6.5 sigma falsification of the Newtonian prediction, where we would expect the same number of stars here and there. So that's an issue. It could maybe be that this cluster had an encounter with something which perturbed it, and so we now have many more stars in the front than in the back. This was studied by Hrabkova et al. And basically excluded, because you need a very massive, quick perturber, and this massive perturber of a mass of about 10 to the 7 solar masses would leave a trace in the kinematical field of the galactic field stars, which is not there. There is no such evidence for any such perturber at all. And so we ran Milgromian models. And this is a model of the cluster, and remarkably, we see an overdensity here too. Okay, and that's a shock, because we now see Mond in the sky. And here's now Jan van Altenburg has developed the first ever direct n-body method, a code with which we can calculate a star cluster in Newton and Milgromian gravitation. This is a real breakthrough, so it's published in this paper. And so here you see a Newtonian cluster, XY, so the galactic rotation is up, and the galactic center is to the left here. This is viewed again from the top, like that orange box. And this is now exactly the same setup, but in Milgromian gravitation. And this is the time. And so you can see that this is later. The cluster grows tails through the two-body relaxation process, basically the energy equipartition process within the cluster. And as time progresses, you can now nicely compare the tidal tails of both cases. And you can already see here that this tidal tail is longer, and you can see this overdensity here. And that's not evident in the Newtonian case. Here they are statistically the same length. Here we have a longer tail and more stars there. And so on, it continues, and we can see here at the end of the calculation that this front tail is much longer than the back tail, but not in Newton. And we have a beautiful symmetry in Newton. So how does this work? Here we have now a setup. This is our star cluster, and the galactic center is to the right. The cluster is moving upwards, and the gravitational field around this cluster is given by this quantity. So here is the distance from the cluster in Mond radii, which is just that distance where beyond which Mond becomes important. And this is the Newtonian case, where at each point we divide the restoring force by the Newtonian value, which is why we have 1 everywhere. So this is the purely Newtonian case. And in this case, we expect there's full symmetry, and so we expect each star, which is unbound, to have an equal probability to leave to the front tail or to the back tail. And this is confirmed by simulations, as I've shown before. So we expect in Newton that the number of stars here and there will be equal within Poisson uncertainties. In the Mond case, or in the Milgromian case, it's a nonlinear theory of gravity, and so now we have a boost of gravitation, which is why this is typically red, so we have more gravitational restoring force. It's as if this open cluster has made a little dark matter halo around it, but this restoring force is not symmetric. It's much bigger towards the direction away from the galactic center, so a star which is unbound, orbiting in this potential, will find a stronger repulsion from the escape and an attractive force back to the cluster on this side, which is the side away from the galactic center, and much less so on this side. And so what happens is that the number of stars which can lead through this inner Lagrange point versus the number of stars which can lead in the outer Lagrange point is now not the same anymore, because the potential restoring force is different. We expect many more stars here than in the backtail. And that is exactly what is observed. So just to be careful, one could argue Teresa Rabkova was a student of mine, and so there's some sort of impact on me, you have to show Mond or so. So we looked at 6 different teams, different publications by 6 different teams, looking at 4 different star clusters, Hyades by these people, Praesepe by these people, then Cohen Gaia by these people, Coma Berenice by these people, and then again by these people, quantified given the velocity vectors and the number of stars which these people have in their publications quantified. So we just took their data, and we see now that, following Jan from Altenburg, we defined the statistics. So this is the normalized distribution of the asymmetry. In Newtonian, given the total number of stars detected, we expect this distribution with this width around the symmetry, so equal number of stars in front and back. And what is actually found is this asymmetry. So many more, significantly more stars, so with nearly 9 sigma confidence difference from this symmetry, we find this asymmetry. So the observed tidal tails are in nearly 9 sigma tension with Newtonian symmetry. We can run models using Jan's code on this, we can see here, this is now a Newtonian model, and then that calculation, indeed a snapshot with this type of property, with these stars in the leading and trailing tail, is consistent with Newtonian gravity. So modeled Newtonian tidal tails are in 0.21 sigma tension with Newtonian symmetry. Well, that's a consistency check. The method works. In Newton we have symmetry, and that's what we also recover. If we now turn on the Milgromian case in Jan's code, which is what he did in his publication, we can see a asymmetry. So this is what we expect from Newton. That's what we get in the Milgromian calculation, and this tells us that the modeled Milgromian tidal tails are in 8.63 sigma tension with the Newtonian symmetry. Now look at the similarity between these numbers. Basically, this deviation is exactly what we see in the sky. And this is rather dramatic, because it really tells us that the evaporation of stars from these star clusters unambiguously, compellingly, and absolutely falsify Newtonian gravitation, well consistent with Xavier Hernandez and Kyung-Hyun K's work on the very wide binary stars. So consistency of test results, falsification of cold and warm dark matter particles, the first part of the talk, implies gravitation cannot be Newtonian, and the tidal tail asymmetry plus very wide binaries confirm this. So we have an excellent, a very beautiful consistency here in the scientific method. And so at this point, a serious physicist will drop their pen, turn by another 90 degrees, and start thinking about cosmological models. And so this is now, and actually realize that Mordecai Milgrom was right all along. So we have seen that the Winnie-the-Pooh Chandrasekhar dynamical friction test falsifies the existence of dark matter particles. please redo the calculations. You're all scientists. You can sit down and do these calculations. You don't have to believe me, right? Now the title tells of open star clusters falsify that gravitation is Newtonian. The very core of the standard model of cosmology is thus completely kaput. It is therefore not surprising that even the interpretation of the cosmic microwave background turns out to be fallacious. So we are now coming to this point. This is the key observational evidence of the model. And my colleagues are telling me this CMB is God's signature in the sky. That's what the universe did. It's undiscussable, and that's just what every cosmological model, whatever you think of, any cosmological model must be consistent with the CMB. So is the Planck CMB solution truly universally valid for all cosmological models is now the question. Which initial conditions to use in cosmological simulations? So what we do is, so it's currently thought that the fluctuations in temperature of the CMB are the initial conditions at that redshift that any cosmological model must fulfill. So we have this God-given CMB basically, if you want. We take a linear structure formation model, for example, lambda CDM, or a Mond-based cosmological model without dark matter, and then put the density fluctuation which arises from this linear structure formation into a computer code like Ramses, the Illustris code they're using, trying to think of those codes now, and or the Phantom Ramses code, and then do the non-linear structure formation to see how galaxies evolve in this. But this is the undiscussable initial condition for any model which we use along this way, okay? And that's what has been told to me, because I'm interested now in doing models without dark matter, but I have to use the CMB. So I started to think about the CMB, and so we did construct new HDM cosmological models which are based on Mond but do not have cold or warm dark matter. So that's the CMB power spectrum, and you can see that yes, we can construct a non-dark matter model with Mond gravity, Milgromian gravity. That's this one here. That's the standard model with dark matter, to get a basically equal fit to this power spectrum. Okay, so yes, you can do it. You can find initial conditions for linear structure growth and then do your structure formation simulations. The problem is this doesn't work, as I've shown, because there's no dark matter, plus the galaxy population actually is incorrect. This also doesn't work. I mean, we did all this, and what we get in the computer does not look like what we see in the sky. We see far too many, far too massive galaxy clusters, and galaxy formation seems to begin far too late. So this is apparently also not a viable model. So I'm telling myself, well, what other options do we have? Well, what about the CMB?
So can I ask a quick question if you don't mind?
Yeah.
A standard model of cosmology with the cold dark matter subdominant on galactic and subgalactic scales, but important in this picture, can that not be arranged? The hybrid, so-called hybrid model.
No, it can't, because you need the cold dark matter in the corresponding density and amount to explain these peaks.
I agree, but that we invoke Mond on galactic and subgalactic scales, but we
yes.
invoke dark matter here.
So in this model,
No, the left one.
Yeah, this one, the new HDM model has
No, the other one.
left ones. This is just a standard cold dark matter.
Yeah, so I tinker with it in such a way that dark matter does not show up in those regions where the rotation curves are flat. It is maybe sent to the outside outer halos, but Mond controls galactic dynamics where the rotation curves are flat, but dark matter controls structure formation here. I'm just trying to see if there's a way out.
Well, I mean, you have to arrange your dark matter in such a way that it doesn't do dynamical friction, or at least to reduce it so much that it doesn't play a role, because
Yes.
that's okay. And then, I mean, if you try to do that, such a hybrid model, then you're talking about a completely different type of model, and that has not been investigated. So you'd have to basically construct such a model, probably try, like as a first instance, to match this data, and then structure formation simulation to see whether that works. But here currently, we are only testing this versus new HDM. And
sure. Thank you. Yes.
both can be constructed to, and so new HDM is with stellar neutrinos, which is like a hot dark matter component. So that's basically what you're saying. Plus MOND takes the role on the small scale, so basically on the galactic scales. Yeah. And so both can be arranged to fit this power spectrum. But is this correct? Should I take a MOND-based model and actually assume the CMB power spectrum as an initial condition? So here's this situation. Imagine the photosphere of the hot Big Bang leaves a CMB signal which has no structure whatsoever, just as a Gedanken experiment. Then the photons propagate from the surface of last scattering to us, and we see it today at a redshift of 0. So along the way, these photons are deflected through weak lensing, so they're propagating and now structure forms, and so they're deviated by the structures as the structures are evolving in the adopted model. Then they change the energy through scattering on electrons which accumulate in these structures, and this depends on the time. And they change energy through the development of the potential wells, because as the photon enters, the potential well changes, the photon leaves with a slightly different energy. And there are new photons from a foreground, which of course, galaxies are born and start shining. And then we observe the CMB, and then we have to correct for all of these effects to get the fluctuations at the redshift of 1100. But these corrections are model dependent, because in a hypothetical model in which I form structures, very massive structures very quickly, each of these effects will be different and the corrections will be different, which means if I take what I observed today, I do the corrections for this other model, I get a completely different type of CMB and a different power spectrum. So the initial conditions at this redshift must be recalculated for every cosmological model separately. And this has actually not been done. So given the CMB observed at this redshift today, every cosmological model has its own unique CMB power spectrum at when recombination occurs in that model. It could be at a different redshift, not 1100. And so, but is the CMB, so that's the one point. So this exercise of constructing a MOND cosmological model and forcing it into the currently published Planck power spectrum is logically incorrect. I first have to figure out what sort of power spectrum I get from the observed CMB in order to do that calculation. And so that must be an iterative process, and this has not been done. So, but then another issue arises. Is the CMB actually truly the surface of last scattering, the photosphere of a hot Big Bang? Because now it has come up that there's an hitherto unknown foreground, and those are forming elliptical galaxies and the CMB. So the foreground to the CMB are from forming elliptical galaxies. So now consider nuclear reactions. I mean, this is a diversion one has to do. We have the proton-proton chain, which makes helium in solar-type stars. And as you know, this combination of two protons leaves a helium nucleus and produces a gamma ray photon. So hydrogen-hydrogen makes helium ultimately and produces quite a few gamma photons on the way. Then in slightly more massive stars, once we have carbon, nitrogen, oxygen, we have the CNO cycle, which also produces helium and photons. Then we get from just helium, we can produce carbon through the triple alpha process, radiating mega electron 1 photons. And here's what is, you can get this from Wikipedia. So that's the temperature in the star, that's the sun does the PP chain. The PP chain liberates energy. That's why the sun is shining. In slightly more massive stars, we get the CNO cycle, liberating even more energy per reaction. And once we get to the triple alpha process, we can also generate much more energy. And then once we have carbon, we get into this alpha ladder process, with which we create successively the more and more massive elements. And at each step, a gamma ray photon is emitted. So that's why when we now look at the energy, so this is the average binding energy per nucleon as a function of number of nucleons. So we have here hydrogen, of course 0, lithium, and then oxygen, iron. We see that this is the peak. So when we synthesize in stars up to iron, we release energy, and of course everybody knows that. And this is the exothermic regime up to there to iron, and that's why stars shine. Now, to get to these high elements, you need massive stars between 10 and up to more than 100 solar masses. And while they are doing this, they produce a luminosity of 100,000 to a million solar luminosities. So the sun is today 1 L sun, they would be 10 to the 5 to a million solar luminosities. So they are hellishly bright. And now let's look at an elliptical galaxy. This is an elliptical galaxy today. The most massive ones formed fastest. We know that from the properties of the stars in them. And they formed very early. The most massive ones formed earliest. The less massive ones formed a bit longer and a little bit after. Then contain about 10 to the 10 solar masses in metals. That has to be synthesized, and you need stars to do that, massive stars. To produce this within less than 1 billion years, because we know that's how quickly they formed, they must have been 10 to the 15 solar luminosities bright. So this thing was 1,000 to 10,000 times brighter when it was actually being born. And that's only possible if the IMF for the whole galaxy was top heavy, had many more massive stars than we see in our galaxy today. So we know that they have very high alpha over iron abundance ratios, which means they formed very quickly before supernova 1A contributed iron. That's how we know they formed quickly, because supernova 1A contribute most of the iron, and that would reduce this ratio. They are very metal rich, so they needed to have very large star formation rates of 1,000 solar masses per year with a top heavy IMF in order to actually make those metals. Without both of these, there's no chance to get those metallicities. The observation-induced formation timescales come out from collapsing protogalactic gas clouds from radii of 1 kiloparsec. So we know how quickly they formed. We know how this formation timescale depends on the mass of the galaxy. And from that we can deduce, this is called the downsizing relation. And from that we can calculate that you needed clouds, pre-galactic gas clouds, which had a radius of 400 kiloparsecs, which were in free fall to form the elliptical galaxy, and then you get exactly the timescales. And you need to do that in Milgromian gravitation. Now here's an actual measurement by Yegathisan et al., published 2025, of 3 elliptical galaxies, and we have here the mass-weighted, light-weighted ages. So they did a pixel by pixel spectral energy distribution population synthesis, and also which gives them also metallicity map in the galaxy. And you can see that the galaxies started forming stars at a time before the Big Bang. Okay, and they are very metal rich. You can see here this is solar, and the inner parts are supersolar. These parts are solar. So on a galactic scale, you had to enrich the galaxy to solar metallicities at the time before the Big Bang, basically. So this is the growth curve. Here is the mass as a function of time. Let's look back time. This is the nominal Big Bang. These are the growth curves from the data I've just shown you from Yegathisan et al. And you can see that they started to form before the hot Big Bang, according to their solutions. And now we constructed models with Eda Giorgo here of such growth curves, which is what we need for downsizing to make these metallicities with the top-heavy IMF. So these curves come out of the need to explain the metallicities and the downsizing time in these galaxies, and these are other curves. And it turns out that these type of star formation rates are observed. So this is a paper by Nguyen et al. Looking at a redshift of 4.8 ALMA sources, and they observed these are quasi-host galaxies to have redshifts, star formation rates at these masses of these systems of exactly what we need, 1,000 to a few thousand solar masses per year. So this is what the ellipticals which we see in the universe today looked like when they were forming. And in elliptical galaxies, the stellar IMF must have been top-heavy. So this is the number of stars versus mass. This is one solar mass. In our galaxy, we have the canonical IMF, basically. In an elliptical, we absolutely need a top-heavy IMF to make all those metals. And that's why these ellipticals were phenomenally bright. So this is the luminosity evolution as a function of time. The galaxies begin to be formed here, then the luminosity increases, peaks at the peak of the collapse of the gas cloud, and then the star formation subsides. These are different calculations with different codes. They achieve a similar peak luminosity, as you can see, for different galaxy masses here. And these galaxies, when they were at this stage, they would not be visible because they would be hiding themselves in dust. So this is the spectral energy distribution of a star forming a galaxy from this review here by these people. You can see that any typical star forming galaxy radiates mostly at 0.1 millimeters because that's at the dust. And any starburst immediately shrouds itself in dust. So these ellipticals would have been radiating in their rest frame mostly at that wavelength. So the pre-galactic gas cloud collapse simulations tell us that we needed these gas clouds to collapse from these radii to be consistent with the downsizing times. The present-day distances between elliptical galaxies are about 15 megaparsecs. Therefore, you go back in time until these protogalactic clouds touch. That was a redshift of about 19. And when you put that together with this wavelength, you see that they would be radiating at 1.9 millimeters, seen today, which is exactly where the CMB peak is. And this is a remarkable coincidence, if we call it a coincidence. And recently, just now, Eda pointed out to me this paper, discovery of red galaxy candidates at redshift of about 12, early dust growth or significant nebula emission. So this is already starting to confirm, yes, these starbursts at a high redshift are in the dust enshrouding. So we calculated the photon energy, which we should see today as a consequence of these processes. So this is now the redshift. This is a redshift of 1000. That's the nominal hot Big Bang CMB, which radiated with that energy density. As the universe expanded, the energy density of the photons decreases. The photons are also redshifted, so the peak of the Planck curve goes to longer and longer wavelengths. At this time, the elliptical galaxies formed, and they contributed this amount of radiation too, which just happens by chance to come out to be about the same energy density. In fact, the first calculations we did gave exactly the energy density of the CMB, crazily. And we have to make adjustments to push it down as much as we can, and then we are at about 1% of the CMB background. And that's already violating, like taking the galaxies to a much larger distance than they are. So the thing is, the galaxies formed around this redshift, then they will be contributing the CMB. So you don't need this. You can have just ellipticals. They contribute a CMB. You don't need the hot Big Bang, according to these calculations. And so average separation between elliptical galaxies today is about 15 megaparsecs. Average separation between elliptical galaxies at that redshift is about 0.8 megaparsecs, which means we expect about 6 massive ellipticals in each Planck pixel at that redshift. And that means, yes, the background is fairly uniform. because of this large number of ellipticals. Therefore, this indicates, I mean, if we have to at least subtract the contribution of this foreground, and that leaves basically nothing. So it turns now out that the Planck CMB is most likely not actually a hot Big Bang evidence, but it's the formation of the ellipticals. Is that the case? Well, at least highly significant contamination of the cosmic microwave background by this hitherto unknown foreground. So is there no hot Big Bang? That's the basic question which we now have. So we have the situation we have as time progresses, the CMB, the afterglow of the hot Big Bang, then the photons get redshifted, and today we see the CMB. In addition to that, we do have the birth of Early-type galaxies, which also contribute. And now we have the problem that this contribution amounts to basically this contribution. So we have to subtract this foreground, and then basically nothing is left. And here's reinforcing evidence, and I'm now basically finished, just as this final point here. Remarkably, the CMB, as it's observed today, has more power in it at higher temperature on the southern hemisphere. This is discussed in literature. We discovered some time ago, unknowing, at that time this was unknown to me, much more than 5 sigma larger number of early-type galaxies on the southern hemisphere than on the northern hemisphere. This is crazy. And this is the map. So each point is a galaxy. You can see that this is the ecliptic here. You can see that in the southern hemisphere we have a significant overabundance of early-type galaxies. And we thought this is some catalog issue, but we cannot identify a catalog issue so far. This seems to be a real asymmetry in the universe. Remarkably, so this is that map, the asymmetry in the CMB, it has more power in the southern hemisphere. So this here is the ecliptic, basically this curve here. You can see that this overabundance of the higher temperature here coincides with this stripe. And even this spot here seems to be some sort of evidence. I don't know. But this is remarkable because it would connect the CMB to ellipticals, possibly. Furthermore, it would tell us that the ellipticals which we see locally extend out to the horizon, because that's nearly basically where this emission comes from. So we are looking at a cosmologically scale asymmetry, inhomogeneity of the universe. So neither the CMB nor the Planck CMB power spectrum are therefore related to primordial inflation-driven fluctuations. The reason I'm putting this now as a fact is simply because of the elliptical galaxy foreground. If it's at 1% subtraction from a background which has fluctuations at the level of 10 to the minus 5 means that the 10 to the minus 5 fluctuations on which the power spectrum is based has no physical content. That's why I have this statement here. And so to the conclusions, the dynamical friction test tells us there is no dark matter. The many independent tests, excuse me, on few thousand to gigaparsec scales unambiguously show the dark matter-based models to not be relevant for the university. We are at a likelihood where I would say no serious physicist can still entertain that model. Okay. The tidal tails of open clusters plus the very wide binary stars tell us that gravitation is Milgromian. This is inescapable given the data. Hitherto not recognized foreground, the elements synthesizing massive elliptical galaxies tell us that CMB appears to have a different origin, at least a large fraction of the CMB. And more details at another opportunity. I would like to say here that the discovery by Mordecai Milgrom in 1983 of A0 constitutes one of the greatest scientific discoveries made in the 20th century. It leads to the prediction of the baryon-Tully-Fisher relation and to the radial acceleration relation, which are fundamental relations of galaxies, and this was predicted by Milgrom at that time. only fools would deny that. Okay. And ultimately, this then leads to a radically different cosmological model, which we are cooking up now with Ella Georgo and some others. And these are the conclusions. So thank you for listening. You're muted, Teinder.
I'm sorry. Yeah, thanks very much, Pavel, for this very interesting and thought-provoking lecture. Yes, yeah, great. Already there are. Bernd, go ahead, please.
But you can start, Chajinder, if you want.
No, I will wait. I'll wait. Pavel, your hand symbol is
It
activated.
recognizes, yeah, I should switch that off, sorry.
Yeah. Bernd, how are you? Go ahead.
Oh, I'm fine, thank you. So, first of all, thank you very much for this incredibly interesting and provocative talk. My question, well, basically I have a lot of questions, but from epistemological point of view, because you said that we have a quite peculiar situation that a model is advocated by the majority of astronomers and cosmologists, which has, to put it mildly, many flaws, or which is quite falsified. What I see at the moment is a kind of epistemological dissonance. We have many tests of general relativity, so the theory of gravity, on which the standard model is based. Even in a strong field regime, think of pulsars or black holes, and the theory passes these tests. And I think this is one of the reasons why many people stick to the dark matter and dark energy model, because this does not require modifying general relativity. On the other hand, we have many observations which seems to be in conflict with this very model, and this is something, yeah, I find hard to understand. And my question would be, how would you assess the situation?
Oops. Sorry. Yes, that's a very, very important question indeed. I'm completely aware of all these tests of gravitation, which are, of course, very serious, and that tell us that in the regimes they are being done, that's where Einstein's theory of gravitation is working extremely well. Now, a test doesn't prove a theory, it just enhances our confidence. But this is no excuse for the community, I'm afraid to say, because it just means we have to think harder, right? I mean, yes, on the scales where GR is tested, which is neutron stars, black holes, it's a great success. On the tests where it's tested on galactic scales, it fails because you need to then invoke dark matter. So that theory actually fails. The dark matter approach has been very important. It's a very important and serious scientific hypothesis to postulate that there might be additional dark matter particles which are exotic, which are not currently covered by the standard model of particle physics. It's a very reasonable hypothesis, and one had to work with that as a first ansatz. But it's been falsified. That's out of the window. There's no point in going back to that. It's simply it's a waste of time, and in particular a waste of taxpayers' money to continue entertaining that idea. That's out of the window, and I wouldn't touch it at all anymore. Only non-serious physicists still do that. Sorry to say that in these very clear terms. Yeah, but this simply means now we need to do research on why is GR so extremely well verified in those regimes. Why does it apparently fail? And I'm emphasizing apparently. Why does it apparently fail in the very weak field limit? And that's where we have to do research. So that's why this discovery by Milgrom of A0 is a very serious hint for us to understand that there's something deep about the cosmology and about the universe, maybe about gravitation, we don't fully understand. And the problem is currently that by saying GR is verified, that's the theory, and therefore I believe in dark matter, because it is just a question of religious concept belief, because it's been falsified logically, so you can only entertain this with the unscientific concept of belief, and that is blocking further research. So young people today are discouraged to investigate this issue of why is GR apparently breaking down, or is it really breaking down, or is there something about GR we haven't fully understood yet? They are blocked by this institutional-wide dogma of only allowed to talk about dark matter. In the United States, it's extremely problematical. Here in Europe, it's a little bit more liberal, but it's absolutely catastrophic the way the young people are educated today, and that's the damage. That's the problem which I see. This is the crisis. Not the crisis that there's no dark matter. The crisis is the way young people are educated to simply not look in a particular direction. I mean, I've been just recently told, I'm trying to remember who it was, but one shouldn't anyway name names, I guess. But I was told somebody who's working with me has a friend in the University of Oklahoma. There's a team there looking at the very wide binaries, and Xavier will be interested to hear this, and maybe Xavier knows who that is. I don't. I haven't checked them. Those people. So I asked the person who's working with me. I asked, how will they deal with this non-Newtonian effect, and will they actually also discuss Mond? And he told me that no, they do not at all discuss Milgromian gravitation. It's forbidden in that group apparently, and that is the, I would say, scandal. It's not even a crisis. It's actually completely scandalous that this is even allowed to be done. And from my point of view, such research groups need to be closed down, because that's not science anymore. That's pure dogma pushing something which is highly non-scientific. That's the problem.
Okay.
Yeah, thank you, Pavel. Actually, I wanted to just make a comment.
Thank you.
I do not think the most important question is why general relativity breaks down. No, the most important question is, what is the relativistic generalization of Milgrom's Mond, which reduces to general relativity at high accelerations?
Yeah.
This, I agree, not many people are working on this problem, but the solution has to be also very neat. It has to tie in with the standard model of particle physics and general relativity and the overall set of forces in a nice way. It makes a good quantum theory, a good renormalizable quantum field theory. I think, to my understanding, that's where the big gap lies right now. We have to find that theory and do cosmology with it.
Exactly.
And show that everything works. So I totally agree with you that there is a very fierce and strong dark matter dogma. When I hear a particle physicist give a talk on detection of dark matter and such detector, I ask them, but you have problem on galaxy rotation curves. Oh no, I'm not an astrophysicist. I'm looking for dark matter in the lab. So we are in that unfortunate situation where people are not able to cross-talk with each other. Yeah.
Well, but you're raising an important issue, and that is, how do I now start developing such a theory, right? And
Yes.
there have been some very nice, there's been significant progress. This by Bekenstein, TVS, and then this by Skådis and Slozhnik. Now, here now the problem arises. These people are trying to develop a relativistic formulation, which includes Mond and leads to the appropriate Newtonian GR limits and the Mond behavior in the appropriate limit, subject to the condition that this description of the cosmological model, which is incorporated in the equations, must fulfill the Planck power spectrum.
I agree. I know these words.
And that is already wrong, right? Because if you do such a model, then you first have to check how is my structure formation, then recalculate the power spectrum, if there is even that event in that theory, to that redshift whenever it happened, and then do this iteratively to actually then adjust the theory to the new power spectrum, which one would calculate, assuming there's a hot Big Bang. However, one has to take into account elliptical galaxies. They do contribute photons. That is simply, that's just nuclear physics. And that has also not been done. And so you can see that this Skådis and Slozhnik model mathematically an incredibly amazing advance, but it basically has little meaning in the sense that they force this whole theoretical description into a data set, which is the Planck power spectrum, which has no physical meaning. It has no physical meaning.
Yeah, I think, but that, Pavel, is a later development due to your recent work. For example, the Slosnik and Scottis was few years ago. My point even about their work, I know their work, also Bekenstein, is that it is still a kind of relativistic phenomenology.
Sure.
We are talking of fundamental physical forces, strong, electroweak, general relativity, how to unify them as, unitary gauge invariant theories, which are a good quantum field theory behavior. To me, those principles are missing right now. I'm not saying they're not there. I'm certain they're there, including also this very beautiful point which Motim emphasizes. Mond is a consequence of scale invariance. So we need a scale invariant generalization of general relativity, which quote unquote should also be beautiful. It should, yeah. So that's where I don't fully agree with the philosophy of Scottis, because it is, to my mind, being developed in isolation. We have to keep in mind particle physics and gauge theories, and in totality come up with something nice, which is a scale invariant generalization of general relativity.
Well, that's what one needs the young people to have the open door and
I agree. I agree.
try. I mean, how did Heisenberg or Schrödinger develop their
Yes.
wave
Yes.
dynamics? I mean,
Yeah.
how did they do that, right?
Yeah. People with that kind of expertise are not looking at this kind of problem. These people would be field theorists, particle physicists, string theorists, all willing to imbibe Mond into a relativistic theory. But like you said, people with that expertise don't want to entertain this possibility.
Yes,
Bernd, you're saying something?
yes.
I posted something on the chat, which is
Okay, let
admittedly a
me.
heretical question. Could it be
May
that
I
all
dare to ask whether we might have misinterpreted other data which we think supports either the Big Bang model and or general relativity? I don't know. I don't know how to answer that.
Well, I mean, this the other important constraint is the expansion. So you go back in time, and of course, that leads you to a dense state, which of course is a very strong argument for a hot Big Bang. And so can we think that the redshift is expansion? And I think at the moment I don't see any reason why not to think that, right? So I'm working in the framework that the universe is expanding. I'm not challenging that. Nevertheless, we should still keep open our ears to the possibility that some people might consider other avenues, tide light and so on, and allow them to develop their ideas. As long as it's rigorous. And
Yeah.
yeah, so.
There's a comment from Igor Kanachiko, who gave a talk at OSMU a few months back. Igor writes that A naught lambda and their interrelation and the Mond law are derived from quantum fluctuations of spin connection described by pre-canonical quantum gravity in our recent paper. For example, dark matter and dark energy as manifestations of quantum spin connection form. The relativistic Mond could also be derived within this framework. I agree. So efforts are on. I agree with that. Thanks, Igor.
So exactly. So the discovery by Milgrom, this epochal discovery by Milgrom of a zero in the data in 1983, or publication 1983 of that, is exactly leading to the must be leading to the investigation of all these type of ideas. And yes, I do think there is a connection to even to quantum field theory, and that needs to be investigated. We need people who are interested. They should, and they have ideas. They need to go into this direction.
Yes.
That's because otherwise we will not make progress.
I agree. I totally agree. I also try, I work on this, but not much success. so far, but I'm looking at it.
So am I. No, I mean, I wish also I could come up with the theory, but of course also not. No? So
Yeah. But I think that's what in my opinion, why we face opposition, and the opposition, so to say, gets away with it because we don't have the relativistic theory yet. If we have that, and if we do cosmology with it, taking into account all these new developments, Webb early galaxies, elliptical galaxies, pollution of the CMB because of that, contamination. And I think, yeah, once we have that, we will be on a much stronger footing, which we already are right now. But so that's where, I mean, people tell me that, okay, your Mond is very good at galactic and subgalactic scales, but how will you form structure? So they don't like this Scottish model kind of model, again for the same reason, because they want a good theory. Um,
well,
so
that's the challenge that one is to find a good theory, right? That's what we have
yes,
to
yes.
work towards.
But so that's where people suggest that maybe a good theory will include some dark matter component and a Mond component. This I am undecided about right now.
I think rather than many of us who will not be successful in finding this theory, because it is a major intellectual challenge of the equivalence of what Einstein did, Heisenberg, Schrödinger. This is the major thing. But what we can do is work with Mond and look at galaxy evolution in Milgromian gravitation, for example. How do star clusters evolve in Milgromian gravitation? And then learn more about how these galaxies evolve. That's something which many people can do without trying to solve the really huge, big problem. And even that is basically not possible, right? Because you don't get money to find, or at least it's very difficult to fund students and postdocs to do simulations in Mond. You apply for a Mond grant, and it's more likely to not go through than if you try to do a sort of more standard type of application. So that's also a problem. We need more normal research, normal, which does not mean it's lesser value. In fact, it's extremely of extreme value. How does a galaxy now actually evolve if the universe is Milgromian? Nobody knows, right? It's not been investigated. How do I even set up a galaxy so that the galaxies which I get in my computer, which evolve, have star formation, look like the real thing? I mean, when we set up galaxies, we take a Milky Way, put it into the computer, it breaks up in Milgrom. Obviously, but that's because we're taking a finished thing, we're putting it into the computer, into a fully self-gravitating system with Milgromian gravitation, which effectively is stronger, it's nonlinear, and of course the thing first goes haywire because it's not actually in equilibrium. So you need the galaxies to actually evolve and grow in Milgromian gravitation, and nobody's done that. I mean, we know how to do it, we can do it, we have the codes, but not the funding. So that's the type of research which is also essential to build up knowledge how galaxies evolve and form and then we can deduce how did they form, and from that deduction that will help us get new information on the initial conditions when galaxies actually started to evolve, which is crucial to developing the big theory.
I agree. Thank you, David.
Right. Thanks, Jitendra. Thanks very much, Pavel, for the talk. It's just a question that comes to mind listening to the discussion. So, Pavel, in the talk, you mentioned that particle-like dark matter is ruled out. I'm just wondering, do you think that if you maintain the Einstein field equation, that any form that you could put into the right-hand side, any kind of matter, any kind of energy momentum might account for these effects? Or is any kind of sort of matter or energy or any kind of energy momentum kind of correction or addition to the Einstein field equation ruled out by these things? Because you focused on particle dark matter, but are there other possible options in there?
Well, there are ideas based on fluid dark matter, and
I'm sorry, I didn't catch.
There are ideas based on fluid dark matter where you have some sort of Yeah, I'm forgetting the details now, but where this fluid changes properties,
fluid.
it becomes Milgromian-like within galaxies, and sure, why should one not investigate those? That's possible, but they are very different to lambda CDM, right? So again, it's the same statement I made before. I think it's valuable to investigate such models, but you cannot start with the CMB unless you've shown that that same CMB is valid for these models, because structure formation will be different. And that changes your 10 to the minus 5 level fluctuation and will have an effect, potentially a drastic effect on the power spectrum. Furthermore, the elliptical galaxies have to be taken into account as a foreground. So how do you start such calculations? And that's what one would have to do properly. The people I know who do these type of models always think the CMB is this guard signature in the sky, and they will start their investigation from there, and that's something they have to get away from. That's just not valid anymore.
This is a new development, Pavel, isn't it? Last couple of years, this elliptical foreground contribution.
We brought this up now in 2025 with Eda Giorgo. Eda Giorgo did the calculations, and it's a paper published Nuclear Physics B.
Okay.
And, yes, this is a new thing, but in principle, this should have been known for a long time, because there are experts studying elliptical galaxies, and they should have been able to deduce this. But I think nobody dares to go into that direction. I mean, challenging.
Many years ago, Fred Hoyle and I think Jayant Narlikar, they used to talk of iron needles in the interstellar space as giving rise to, but so this is a different story now. This is supported by data.
This is completely different. This is completely different in the sense that it doesn't need iron needles, and it doesn't rest on on a homogeneous or non-evolving universe or static universe, but it's taking real data, yes, and it's just making the statement ellipticals, when they form, they look like any starburst, which we see. That's it, and then you get this result, and I don't see how one can avoid that.
Thank you. Yeah. I'll just read a few comments which have come in the chat. Veselin writes, GR is valid, but it is not reparameterization invariant, so it applies only if the proper time is utilized correctly. In this respect, the cosmological constant and Mond fundamental acceleration are due to incorrect time parameterization. Mond can be justified from SIV, which is relativistic and reparameterization invariant. Thank you. And Rob Wilson replies, yes, it is essential to have two independent time coordinates, or else it is impossible to describe large-scale interactions. Yes, Anastasia, you want to say something?
Oh, hi. Well, this was just about the superfluid stuff. So
Okay.
with superfluid dark matter, like you're still trying to feed the CMB, taking it the fast value, right? So what Pavel did was ERA was like reinterpreting the CMB. So you kind of have to start again with the basic assumptions that you have. And those basic assumptions are not about CMB being what it is, as we know from lambda CDM. So yeah, this just changes.
I remember, thank you. I remember, Pavel, last time at Indraneel's talk, I asked you then, when this point came up, ellipticals, what do you do about helium production then? You said something, could you please say it again?
I think I said it's not an issue, we have it under control. So we are obviously aware of this, and there are many other very, very interesting consequences of the very early formation of ellipticals on all sorts of elements. And Ada is an expert on chemical evolution. She has a complete handle on that, and I think we know fairly well how things work, but it just takes time to do all the calculations. And
you are saying you can make helium, all the helium in stars?
Yeah, sure. Yeah.
Oh, that would really make cosmology stand on its head, right? I'm not saying it's not cannot be, but everything will change.
Yes, it will. It's not that it will change. We are living in a universe which is distinctly non-lambda CDM, distinctly not hot Big Bang.
Okay. Yes. Thank you. More questions or comments, please. Also, yeah, I remember. I don't know if Xavier is still in the audience. You present wide binaries as a case for breakdown of Newtonian gravity in a very confident way. But I'm noticing last couple of years, last 1 year, the presentation is that the whole situation is confused. It's messy.
It's messy, and there's one very important issue to be aware of, which is I think Xavier would want to say it now.
Yeah. Xavier, go ahead, please.
Thanks. Hello to everyone. Hello, Pavel. Hello, Tejinder. Yeah, well, there is this feeling that the situation is very confused with regarding the wide binaries has basically been driven by the appearance of a couple of papers, really 2 or 3 papers, not more than that, by a couple of groups, mostly doing things actually very demonstrably wrong. I mean, actually, one of the recent papers on this thing was published about a year ago now by an author by the name of Cookson, and just a few months ago we published in the same journal with Pavel actually a formal rebuttal to this particular paper, which where they actually had an extremely silly mistake. I mean, they were comparing Newtonian predictions for binaries having a larger mass than the one that was present in the binaries that they were treating. So these kind of things have been occurring and have been led.
Also, did Petordis and Sutherland have a new paper recently?
Yes, well, there is a relatively recent paper by the London group as well, by Will Sutherland and Petordis and others. There you have to be extremely careful, because what their data and their analysis actually show is not that there is no anomaly. If you read the paper carefully, what they find is that the chi-squared value they assign to the Newtonian model is better than the one they assign to a particular model they are testing. Okay. However, the chi-squared value for both those models are unsatisfactory. So they are formal rejections of both the Mondian model they are testing and the Newtonian model they are testing. So that tells you that there's something not quite understood, not quite right behind all this. I'm in contact with them, and there are a number of issues. For example, the lack of a deep Newtonian regime where they can calibrate and they can know exactly what's going on. They've told me they are going to be addressing that in subsequent publications. I hope it's true, and so there are a number of details which I hope they will improve on, and which probably will help to clear the situation. For example, another issue is that the particular Mond model they are using happens to be the same Mond model that Indranil was using, and now Jan Flam-Altenberg in Bonn has shown that in the transition regime between the limit deep Mond regime and the sort of Newtonian regime, the analytic first order estimate of Indranil, which Sutherland and Petordis are also using, overestimates the Mond effect, the Mond anomaly. So that naturally leads to a poorer fit to the data, and this has been done through looking directly at integrations of Mond orbits of stars. No, so I'm working with them as well to try and get some kind of a better calibration for exactly what you would expect. But of course, this is all these things depend very much on the details of Mond. So that's why my approach.
Looks like people are just making life hard for you. They write something and you have to point it out and
Well, to some extent, yes. But I mean, my hope, I'm not aware of this other group in the US that Pavel was talking about. I mean, with Q, I mean, something that, as far as I can tell, the only really remaining outstanding possible, let's say, what's the term? Not statistical, but let's say systematic unknown that was really left there was the idea of that perhaps some of the binary, some of the individual components of each binary might not be a binary themselves, but might actually be a binary themselves. So that would introduce a contaminant, both kinematical and mass-wise, that goes in the sense of boosting the velocity. Over the past year, with a colleague here in Mexico, we've spent more than 20 telescope nights looking at hundreds and hundreds of these individual stars very, very carefully, doing what's called speckle interferometry to basically reach the diffraction limit of the telescope. So we have HST quality seeing on these images, and looking specifically for these supposed hidden tertiaries, and we found an extremely small fraction of them. So, so now we are about to publish a new paper by the end of the month, I'm sure. Extremely important, because we have thousands, well, about 1,000 speckle interferometry checks, directly checking whether the stars we're including are binaries or individual binaries, and only keeping the ones where this doesn't happen, and including also, and this is work that Q and his colleagues have been doing, radial velocity measurements, so extremely high quality radial velocity measurements for a small sample of white binaries. But this allows to go from the 2D velocity on the plane of the sky that Gaia allows, to a full 3D velocity modeling of these binaries, and the results are extremely encouraging. I hope
Thank you.
that paper will be on the archive by the end of the month.
Great. Thank you very much. That looks very interesting. I wanted to ask you and Pavel, is there a review article which presents tidal tails, dynamical friction, and white binaries all together in one scope, saying, look at this. Is there a this kind that might be very useful, no? That
Well, there's this Kroupa et al. 2024, which I wrote with Eda Georgo and Elena Asensio and others, which is a summary of many of these. But of course, since 2023, this has evolved further, this topic, like with the ellipticals now. So there is no review of what I presented here in one manuscript.
okay.
And I did not talk about the very wide binaries explicitly, but the newest results by Xavier and He will come out soon. So then one should be, of course, mentioning or like talking about that, including writing about that in a review. I think what Xavier did not say, what I actually wanted to say, is really an important point which Xavier has been raising, and that is that any such test which people publish must always demonstrate that their method actually gets the Newtonian case in the small AU regime. So like 1,000 AU and below, they must get the Newtonian solutions. And I think usually this is not done. Like Indrani Barnik did not do it, and Xavier is doing it, and that's really important. So you really see that the method, if you really look at systems which you know are Newtonian, you get Newtonian solutions. That's an essential demonstration of the technique.
Thank you. I also wanted to ask you both, is there a new Gaia data release around now or later this year?
No, we are waiting for the data release 4 is expected to occur about a year from now. It's scheduled for December 26.
26, not 25. Okay,
Not
thank you.
25, no. I mean, but what we've done over the past year is to enhance the sample very significantly through independent data sources. But yes, the next Gaia release will occur about a year from now.
Thank you. Thank you. Veselin, please go ahead.
You are
Sorry,
muted.
You're muted. You're muted.
Yeah.
Sorry. I have two questions. I was saying thank you for organizing this meeting. Basically, I mean, Javier, this is wonderful work that you're doing with the wide binaries, but I'm concerned that it would be in kind of no pass or kind of halt like the rotational curves because of the Mont or dark matter explanation, and basically no final decision is taken. But for the CMB, that's kind of interesting point Pavel is making. I'm wondering, do you mean that if you take the foreground out, there is nothing left to explain with the hot Big Bang? And or people haven't done it completely, or
They did not recognize this foreground. They didn't know.
Because I'm looking right now at the CMB with using the SAV theory, and unlike when I was lucky with the Big Bang nucleosynthesis, all the codes that I found for CMB, they use dark matter somehow somewhere. So to remove it, it's very difficult to clear it out.
Exactly. Well, you need to if you develop a new model of, I know you have your cosmological model, which one should investigate, but you need to then do structure formation. So you start with a current power spectrum, do structure formation, correct for that structure formation to rederive a new power spectrum, and then do this iteration. But one should correct, I think Xavier is a bit on the edge, I can see that. The very wide binary test is completely, that's exactly the regime which I mentioned before, that dark matter really cannot play any role whatsoever. So if one sees a clear Milgromian signal, just like with open star clusters, then that is really non-Newtonian gravitation. This is unescapable.
Go ahead.
Well,
And can I just ask my other question?
Maybe Veselin, maybe I think Xavier should respond to what you said about wide binaries, then we can proceed.
Yes, this is an important point, because the object of the whole wide binary test is precisely that you're looking at a regime where dark matter is irrelevant. And the point is that if you take one wide binary in isolation and you say, I observe, or even a population of wide binaries, and you observe an anomaly, you can always say, okay, there's more matter. However, these wide binaries are not in isolation, they are part of the Milky Way disk. And here we have independent constraints on the amount of dark matter locally from the vertical motion of stars in the disk. So this is something, a classical test called the Oort limit from ages ago, from 50 years ago, which has been renewed every so often when the data get better. It's been renewed, retested with Gaia, and the results are extremely stable, and they've been stable for decades. So we know that the local within the disk of the Milky Way, the local density of dark matter cannot be above 10 to the minus 2 solar masses per cubic parsec. Otherwise, the vertical motion of stars in the disk would be inconsistent with reality. So we know how much mass we have in stars. We know how fast they jump up and down, and we know what the height of the disk is. So those three things are related through the gravity model you're assuming. So through Newtonian gravity, or even through Mondian gravity, it won't make much of a difference. That's why you need a halo. You can't put the dark matter within the disk, because then you mess up. If you put enough dark matter in the disk to get the orbit right, the galactic orbit right, you completely mess up the vertical dynamics. You need to put it away in the halo, so that locally you do not violate these independent constraints. So if you find, contrary to what happens with rotation curves of galaxies, the wide binary anomaly cannot be explained by dark matter. The standard, any type of dark matter within the disk is irrelevant. The separation of these things is much less than a parsec. If it were a parsec away, I mean, it's 1/10 of a parsec. So that already means that the amount of dark matter within a white binary is 10⁻⁵ solar masses. That's the maximum allowed dark matter quantity within a white binary. The masses are of order solar mass, so it's completely irrelevant. You cannot explain it with dark matter. The attempt was to introduce sort of stellar dark matter and say, oh, some of your binaries, some of your stars are actually tertiaries. No, some of the stars there are actually, you think they're single stars, they're actually binaries. So that's why over the past year we've really been stressing and spending many nights at the telescope, looking at each of these little stars individually very carefully to see if they are single stars or not, through velocity measurements, extremely high quality velocity measurements, and extremely high quality optical images.
Mm-hmm. Thank you, Xavier.
Yeah.
Now,
well,
okay.
I personally like what is done with the white binary and Mont applications. But what I was saying is that there comes always a paper that says Newtonian gravity is okay, and then it comes a paper saying, no, you didn't do it right. And basically, it's still kind of back and forth.
It's important to know the difference. The papers, there's been one paper which is evidently wrong because they were using a wrong normalization for the Newtonian comparison. But the papers from the London group by Will Sutherland and so on do not say Newtonian gravity is all right. If you read the paper, what it actually says is Newtonian gravity is a better explanation than the particular Montian model we're testing. However, both of those explanations are formally ruled out by the data. And those are studies that do not include a deep Newtonian regime as an internal quality check on the data.
Yeah.
Yeah.
What's
So
happening,
if you take
Xavier,
this as a good
sorry,
point
what's
for
happening is
Mont,
that, sorry, you go ahead.
yeah, then I wonder, I mean, the other strong point for dark matter is the bullet cluster. And I didn't hear from Pavel, how do you resolve the bullet cluster there?
Well, that's another talk. So there's a student here, Dong Zhang, who's actually doing an incredible amount of work on calculating exactly the distribution of mass in the bullet cluster, given all the galaxies, given the intercluster medium, so in the cluster, the intercluster light, so the stars which are not in the galaxies but which also contribute, the gas, lensing, and there is no missing mass problem. And the reason why I'm in Mont, right? So the reason why I'm saying that, and this has not been published, in fact, we had problems with a referee who didn't understand very elementary nuclear physics arguments. The reason I'm saying that is exactly the reason why ellipticals were very bright. They needed to synthesize these elements. That means you need a lot of massive stars to do that. And this is completely inescapable. It's an elementary issue of nuclear physics. And these massive stars, they leave remnants, neutron stars and black holes. And so these elliptical galaxies are full of neutron stars and black holes, which means they are much heavier than thought. And remarkably, this solves the problem. There's no missing mass in Mont. It's exactly right. And this would have been out, except that we had an idiot of a referee who did not understand that concept. And because when you touch the variation of the IMF, and in addition to that, raise issues about Milgromian, the community goes berserk. They go completely mad, and they start arguing by opinion. And then we had an editor in ANA who was on the same category I just said, and the paper was rejected. I'm furious about this. It was not rejected because of an error of argument or calculation. It was rejected on opinion. And the editor, Francois Combs, went along with that. I'm so furious with that, you wouldn't believe it.
Pavel, one thing, so how do you address this question that Mont has a deficit when it comes to explaining clusters?
That's what I'm saying. So in reality, there is simply more mass in these. It's neutron stars and black holes, which are from the dead stars, which produce the elements. This is inescapable. I mean, in fact, this should have been known a long time ago, except that nobody really put it together. There are a few people who do chemical evolution of ellipticals, and they haven't addressed this issue. But this is
There is more baryonic mass in galaxies
yes,
than
exactly.
thought.
It's neutron stars and black holes, and you need them to make the elements. I mean, not them, but the precursor stars.
So this is different from the idea that there might be hidden hot baryons in the
Yeah,
IGM.
this is completely elementary baryonic physics, which you learn in a first year graduate school. You need to do nuclear reactions that leads to dead stars, and those stars populate the galaxy clusters, elevating the mass just by the amount you need. And this was in the major piece of work by the student, and that was rejected. So that's why you don't know about it, because of course we don't put stuff on the archive unless it's rock solid, like, you know, accepted basically. And so I'm furious about this, because this is an essential argument. And Vasilin, you're right to raise that, and also Tender. It's an essential argument which is solved, but it's not in the literature, because there were some, you know, I would use a very strong word here, people who call themselves scientists who actually rejected this paper based on opinion, only on opinion. This is
But
unacceptable.
I'm sure it will emerge elsewhere. It may just take some time. It's a new idea. I
This
think
is
I didn't know this.
unacceptable, because this is a PhD project of a student, and you are talking about the possibility of the PhD failing because you don't have the publication. This is a very serious affront of the scientific practice. You cannot reject a paper based on opinion. This is simply not allowed. And if somebody does it, they should lose their job. This is just something you can't do. Yeah, and this is my reaction to the bullet cluster. Sorry about the strong wording, but I'm really, really loaded up about this.
Thank you, Pavel. Xavier, you were saying something.
Yes, I had just a few comments regarding the bullet cluster, which is generally presented as a falsification of Mond, really. And the argument there, as originally presented, is that you have the two clusters. You see the galaxies in both clusters, they went through each other. Then you have this distribution of gas in the middle, and then you have the lensing signal. And the lensing signal is actually centered upon around the galaxies rather than the gas. The standard argument is to say, well, in Mond there is no dark matter, so then the lensing signal should center around the places where you have the most baryonic matter, which is the gas, and that is not the case. However, that is an extremely naive argument that really implies knowing absolutely nothing about any kind of standard or general relativistic framework, because the lensing signal is not expected around the place where you have the most matter. It is expected around the place where you have the highest surface density of matter. I mean, we see lensing around the sun, and that was measured by Eddington ages ago. However, the mass of the sun is only one solar mass. Nobody will ever detect or try to look for lensing around, say, a 1,000 solar mass molecular cloud, even though it has much more mass than the sun, but it is much more diffuse. Okay, lensing is a matter of comparing impact parameter with an Einstein radius, or an impact parameter with some kind of a modified Einstein radius. And if you look at the bullet cluster, the lensing signal centers around the galaxies. And nobody has ever said that those galaxies are unusual in any sense. They are just the standard elliptical galaxies within the standard framework, standard dark matter halos around them, producing standard lensing around them. So any modified gravity theory that correctly explains lensing around spiral elliptical galaxies will obviously explain or produce the correct lensing centered on the galaxies, which is what you see in the bullet cluster. No, I mean, nobody would really expect. Yes, there is more mass in the gas, about 10 times more mass than in the elliptical galaxies. But the elliptical galaxies at those scales are point sources. So that's where you have a small or the chances of obtaining any sort of lensing. Nobody in the right minds will really expect any lensing associated with the hot gas that has length scales of megaparsecs. It's huge.
Sorry, is this there in the literature? I would be interested in reading this, what you just said.
I can't remember actually. I should write it up, I guess.
Yeah, I think so. Because Moti's explanation, I remember, is different. He has a half a page somewhere on the internet, which I go and which I point people to when they bring up bullet cluster. He was just saying that this is not new. It is the same old issue of clusters and MON having some issue, because, and he thinks he likes the I think the hot baryons in the
Yes, yeah.
electric medium, and I think Stacy doesn't like that. But what he wrote in that half a page was good for me, actually.
Yeah, I mean, Pavel's explanation now would be that this factor of 2 can be made up basically just by looking at the elliptical galaxies themselves. No, if you take account of how much metals they have, then they need to have a factor of 2 more mass. So I mean, when I'm teaching galactic dynamics and looking at the rotation curves of galaxies, you say, well, the mass anomaly here is by a factor of 20. So there's no way you could you can get away with that with the errors in the data, with the gas fractions, with the stellar remnants, whatever. And for years I've been telling my classes, really, if the mass anomaly were a factor of 2, we wouldn't be discussing dark matter, we'd be discussing the IMF.
Yes, yes,
And that's exactly what Pavel pointed out. No, in
yes,
clusters, the mass fraction anomaly is a factor of 2. So
yes.
we can easily explain that by reasonable
One does not.
adjustments to the IMF. No?
We don't say there's a factor of 2 difference. We're saying there are these chemical elements up to iron that amount. You need to explain that. And
I mean,
and by coincidence, they then account for this missing mass. But that's simply because that's how the universe works, right? This is not contrived for an explanation. It comes out of nuclear physics arguments. That's the important thing here.
Yeah, thank you. Anastasia had a comment, bullet cluster is a problem for lambda CDM. Okay, maybe
How did you say that?
Well, it's just that so the problem is with reproducing something like bullet cluster with lambda CDM. So we do know that it turns out to be used as the main evidence, yet at the same time, if you're looking at the simulations, the infall velocity that you have in the bullet cluster is not something you can reproduce with lambda CDM.
Yeah.
And so that's kind of the thing that, well, I guess I asked Pavel to comment on, but more generally that I see in the literature is that this is kind of just, left to be solved in the future, like research. But as of now, we cannot reproduce anything like the bullet cluster, as far as I understand, in our
I think
simulation.
it would be good if you had a note on the archive saying bullet cluster is a problem for lambda CDM.
We actually wrote that paper now. It's in preparation.
Okay,
But
great.
yeah,
Interesting.
so in a sense, and people who have said this are people like Chandrasekhar, who have nothing to do with MOND. So it's not like coming from people who are trying to develop alternatives. Rather, it is coming from people who are trying to just work on cosmology, I would say. And so, yeah, that's been the goal, is like, can you have anything like bullet cluster at all in any cosmology we have now? Actually, we do not, well, okay, I will not take the stage, but we do not have any cosmology right now that can fit both the mass distribution and the collision velocity. We do not have a single model that could explain the bullet cluster at this moment of now, because there are two to one object, you have a set of galaxies colliding, and then you have to explain their collision velocity, and you have to explain mass distribution. In terms of explaining their collision velocity, you have MOND, which explains it better. In terms of mass distribution, you have GR, and MOND doesn't have any so far reliable GR extension to explain it. But their lambda CDM can explain it if you assume there are also lots of problems, because you do have to assume a certain mass distribution before you even talk about the mass in GR. So there are lots of papers about any kind of cluster, any kind of galaxy cluster serving as a confirmation to GR. But anyway, so that's one problem. And the other problem is the collision velocity. And that's something else, that's something that requires you to have a certain structure formation model that would lead you to that collision velocity. And that's something we do not have within GR or lambda CDM. But that's something that Mon can give you a bit better results on. So you like about the body cluster, I think it's a common misconception. So I'm going to state it once again, that if you're trying to talk about the velocities, you are talking about better model based on Mond. If you're talking about mass distribution, like you're talking something about like dark matter within GR. But it is one object. It's one and the same object we're talking about. That's what's interesting.
Thank you. Thank you. Okay, maybe Bernd, maybe the last point.
Yes,
Pavel
from-
said it's much better understood in Mon, but here we do not have a cosmology yet. Yeah, I agree.
Okay. Ha, basically, this is my question. So if the CMB is not the telltale sign of the Big Bang, in which kind of universe do we live? Or are you developing your own cosmology at the moment? So what is the right kind of cosmology? This would be my final question.
Well, that is indeed, yeah, this the sort of question, right? I mean, yes, we
I see. You're
yes,
cooking it up at the moment.
we are. There is indeed, there are ideas, and there is some serious work actually. But it is definitely an expanding case. So the universe is expanding, and
But we are not going towards steady state.
no. So I'm working with this now. Well, Edda Georgo is actually doing currently the development of the equations, and that is very advanced, but it's not published yet. And there are some we are keeping it secret until it's actually published, because there are some ideas in there which.
Yeah. Thank you.
I will not ask a different question. I just have to defend the steady state model a little bit on the conceptual level. It's not a static model, it's an exponential expanding model, the steady state universe. Of Hoyle and Nalikai, they had a de Sitter solution. So they have an expanding universe, just that the density is kept
Yeah. I was just asking if there was any comparison with the steady state, not static, the steady state model.
Yes.
Yeah.
I would want to say that Fred Hoyle.
Pavel, just 1 minute. Could you kindly stop sharing so that we see everybody on the screen? Yeah.
Yes.
Yeah, great. Yeah. Please go ahead.
I was just going to say that many of the ideas of Fred Hoyle were to be taken seriously, I think, of Nalikai too. I think they were very much on a very relevant trajectory. I wouldn't say correct, but definitely very relevant. Fred Hoyle was one of the really outstanding physicists of the last century.
Okay, I just wanted to make sure that people don't. So the steady state, what's steady in the steady state model is the density of matter and the overall picture of the universe. So the matter density stays constant. New galaxies form continuously and new matter forms continuously, but the expansion is exponential. So it's not they don't have any trouble with redshift. They expect redshift. So they expected an exponential expansion of the universe way before the classical Big Bang model. So they were the first in a sense to predict in their cosmological model that the universe is exponentially expanding. Oh, okay, sorry.
Fred Hoyle used to say one Big Bang or many.
Yes, this was Fred Hoyle. One Big Bang or many Big Bangs. And a follow-up question.
Should we take
briefly, does your cosmological model have an origin in time? Or is it
just one moment.
Finite age?
One moment, Bernd. Igor wants to say something. Then we'll come back.
Igor. Very simple question to Pavel, which I encountered in the course of our work. There is certain incompatibility between the interpolation function, which is proven to be successful for galaxies, like a simple interpolating function, and the interpolating function which is claimed to be compatible with the solar system tests, which is like difference between mu1, mu2, and mu20, which is claimed to be compatible by astronomers, you probably know Fienga, and numerical simulations by Niswarny. Those are results from last year. I have seen them. So what would you say, how you would comment about this discrepancy?
Yes, well, the thing is, there's one thing that is, Mond or Milgromian gravitation as we know it today is probably just an approximation to the actual true underlying gravitation, which must be linked with the GR, right? So that is the one thing. And then we don't fully understand this transition. So this transition, the way it's used today, is a poor man's version of doing gravitation in that regime. The other statement here is that actually nobody knows how to do an orbit of a binary in the galactic field. Right? And so this is what Jan Flam-Altenburg is now developing here in Bonn, the actual equations of motion of two stars orbiting about each other. And this also means then a solar system where you have planets, multiple planets going around the star. There are no known solutions, not even numerical solutions in Mond. And so what one does is one transports Newtonian ideas, for example, a conservation of Newtonian linear momentum and Newtonian angular momentum into the Mond case, which is something which is wrong. And Jan Flam-Altenburg is mathematically showing that. There are other quantities which are conserved, which means that the calculations which people have been doing are actually not correct, especially not in the regime where you start seeing Mond effects. And Jan Flam-Altenburg will hopefully publish how to do these calculations properly. This has been highly non-trivial mathematically to actually do this calculation of the exact forces in Milgromian gravitation. And then we will know more. But at the moment, this discrepancy between the transition functions, I would not overinterpret as as something like showing that Mond is wrong. I think that is just would be a completely wrong conclusion. It just tells us that Mond is an effective description and we don't have the true full understanding. Plus also nobody knows how to do these type of orbital calculations. So we know how to do the Newton very well, but in Milgromian gravitation, things change at a very fundamental level concerning conservation quantities. So you need a Lagrangian, you need to show what is conserved, and that changes in Milgromian gravitation. And so then it might look like the transition function doesn't work, and that's simply just because one is not doing the correct orbit integrations. Yeah, so that's one possibility. But Jan Flam-Altenburg would be the person to address this in great mathematical detail. I think, Xavier, you've been also speaking to Jan on this, right? So you know a little bit more also. Maybe.
Yes, I mean, that's one of the things I was mentioning regarding the overestimation of the Mond effect during the transition. That is implicit in some of the analytic recipes that have been used for the white binaries precisely. I mean, from my point of view, this transition function is really just, as Pavel was saying, a sort of zeroth order interpolation between the regimes. You know the two limits, but you don't really know what's happening in between. And if you think of something like quantum mechanics, for example, any particular system you can model in terms of a transition function. If you're looking at things like the heat capacity of crystals or the energy levels of the hydrogen atom, you will always be able to fudge some sort of a transition function between the classical and the quantum regime. But that transition function is not going to be universal, because what's universal is not this transition function at a particular type of system, but the physical principle behind it, no? Comparing action to h bar or whatever. And we don't have the equivalent principle here. So we don't really know what is.
I would, sorry to interrupt you. I would say we don't have the principle even in the quantum to classical case. We don't know if the theory is breaking down in the mesoscopic domain. Maybe it is. I mean,
exactly, but I mean, my point is that without a fundamental theory, even if we actually know or get the correct fundamental theory or not, but without a fundamental theory, these transition functions, I wouldn't really expect them to be universal in any sense.
I
no?
agree. I agree.
So I'm not in the slightest concerned about one fixed transition function being insufficient to model everything in the universe. No, MOND is a zero-order approach. There's no expectation really for these transition functions to be universal. So
I agree.
I don't think that's a serious point, really.
Yeah, Rob Wilson says the real problem is we don't know what space-time is. Yes, I agree.
I would agree. Also add my 2 cents to the opinion of Xavier, that actually we have derived one interpolating function theoretically, which is within 15% close to the simple interpolating function, but it is based on the clearly defined physical approximations, like the point mass fixed in the center. And also it is derived from the second momentum of the equation, which is actually from the first momentum of the equation, which is describing movement of test particle in the random spin connection field. But if we go to high momenta, or if we take the correlations, then interpolating function is different. So we already have evidence that depending on the physical assumptions and the nature of the physical system, the interpolating function will be different.
Oh, that's excellent. That's really very interesting. Yeah.
It will be published, I hope, this year.
Great.
Is there a reference for this latest result you just
For this latest result, there is no reference. We are just finishing the paper now, so probably it will appear, hopefully, this year.
Thank you.
Super.
On archive, I mean.
Thank you.
Thank you for your interest.
Michael, we should start winding up. We have had a great discussion.
We most certainly did. That was an absolutely fantastic discussion. Thank you to everybody who participated. I must admit, I'm moving more and more and more to the conviction that the MOND really is on the point of changing everything, or at least the potential is there for it to do so. Are there any other further questions? It's very good to see so many people here.
I had one.
I just remembered one thing which didn't get touched with little red dots. I don't know.
Yes.
Well, do you want me to get going?
Okay, maybe in the next lecture. Just
I think we have to. Yes.
Just 2 lines and maybe a new talk from you on little red dots. Yeah.
Right.
Yes, well, something related, yes.
Bernd will come back. Sorry, I forgot.
Pavel, thank you very much. It was a wonderful talk. Is there anybody else who has anything else?
Bernd wants to say something.
Just
Sorry,
a brief,
Bernd, go ahead.
do you have a modification of conversation laws in the relativistic version of MOND?
No. As Jan Flam calls it, the Milgromian law dynamics. He's showing that when you formally calculate which quantities are conserved, it is not the Newtonian ones. It's a different type of quantities, and that has to be taken into account when one does orbit integrations.
Okay. So you have new conserved quantities compared to new
different ones. Yeah.
Different ones. Okay, thank you.
Yeah.
That's it.
So, for example, not the what do you call it? The mean. Not the center of mass. The Newtonian center of mass is not conserved, but you have a different quantity which takes that place, which is conserved. Yeah.
Okay. Thank you.
Great, thank you. So maybe we should wind up, Michael.
Right. Yes. Okay. We'll try to get this particular episode up as quickly as possible. Not that we don't try to get them all up, but this one particularly, I think.
Well, Michael, my talk is not up yet, Michael.
No, I know. I'm sorry. We have had some problems here.
Okay.
We just have, but I'll let you know about that later. Yours should be up very soon. I hope both of these talks will be up within the next few days. We have a conference on Saturday in memory of our friend Basil Hiley, who died in January, in Oxford. I have to get ready to prepare for that because it's quite a big meeting. But as soon as that is out of the way, we'll make sure everything's up to date.
No worries. It was just checking.
Thanks very much.
Okay, great. So we say bye to everybody.
Right.
Thanks
Before we do, I hope you won't mind my abusing the privilege, but I was just going to ask, do you mind my asking, Igor, do you mind telling me where you are at the moment? Are you in Albania or are you back in England? You are in Albania. Okay. Right. I'll try and contact you by Zoom. I really would like very much to speak to you. Give my love to Monica and take care.
Thanks,
All
Pavel.
right. All the best to everybody.
You
Take
can
care.
do it right
Great
now.
talk. Thanks for a great
Great.
talk.
Take care. Yes, and thank you, Pavel, again for a great talk.
Discussion.
Thank you
Thanks,
to all
Pavel.
the speakers.
Bye.
Nice to see you.
What will be the
Everybody,
next talk?
Great discussion.
November
See you.
28th.
Hang on, when is the next one?
We have a long gap. Yeah,
We have quite a long gap now,
28th.
don't we? We have.
November 28th, Abhay Ashtekar.
That's right. Yes, yes.
Okay, for the next.
He's our next speaker. Okay. See you then.
Okay, good.
All
Then
the
I
best
know.
to
Thank
everybody.
you. Bye.
Bye.